Alright, this is the third and final segment about Mathematica, integration with Mathematica to be more precise, and we are still in section 1. We talked about subsection 1.1, differentiation, subsection 1.2, syntax for integration. Let's talk about syntax for algebraic manipulation, and this section will turn out to be very, very useful because these commands can reduce a lot of work, a lot of elementary but tedious works. For example, how do you expand a polynomial? Well, expand and an expression. For example, if you have to expand a polynomial expression like, let me type something in, x squared plus 3x minus 4, 4x plus 1, 4x minus 2, 3x plus 5, x squared plus 2. Okay, I have something like that. And you can expand all these by brute force method. You can FOIL it again and again and again, basically. But if it is too tedious, you can simply run it like this with Mathematica, and then it spits out the answer kind of like this. Again, this is a good way to reduce some tedious works. Even more useful command is factor command we have here. Factor, and then you just put in appropriate expression here. Well, we just expanded something, so why don't we just factor the polynomial we have over there? Factor, factor, and then let's just copy and paste that thing. And okay, I don't need this anymore. And if you are given this kind of polynomial, 48x to the 7th power plus 212x to the 6th power and so on, and imagine you'll have to factor this out of just paper and pencil method. It's impossible. Okay, it is possible, yeah, but tedious. But if you put those into Mathematica using factor command and then run it, you have an answer in, well, in matter of instance here. In matter of millisecond, we have the answer. The hard part must be to type everything in, but actually to calculate, it doesn't take too much time. Okay, let's go over to the next command, solve command. This is also a very, very useful command, especially for algebra. How do you work it out? Solve, and then let's type in an equation. Well, we have an equation right over here, so let's recycle this. And then set it equal to 0. And here, you have to use double equality because just single equality is reserved for naming something. Computer scientists already made it, so you have to use double equality. That's the only thing you have to be careful about. Solve command. Oh, actually, no. Did I say the only thing? That's one of the two things you have to worry about solve command. One is that double equality. Second is specifying the variable. So solve it with respect to x. And then we have an answer like this. As a matter of fact, I think Mathematica will understand if you forget comma x. Yes, it did. But if you have more than one character, then you really have to specify with respect to which variable you have to solve. So, for example, you can use solve commands to do something like this. 3x plus 5y over 4xy minus 5z is equals to 1. And now, how many characters are there? There are 1, 2, 3, 4 characters. No, excuse me, 3 characters. So if I simply run it, Mathematica will not understand it. oh, excuse me, it did something. Somehow it just assumed the author is looking for z, so it solved for z. But of course, in order to be more precise, you have to specify with respect to which variable you want to solve. I want to solve it for x and a comma x, and Mathematica will solve it for x. If I want to solve it for y, comma y, and it solve it for y, and then if I want to solve it for z, and then we get the answer kind of like that. So solve command is useful, and it requires a bit of a practice. Another important command, okay, as a matter of fact, as far as the importance is concerned, first three commands, especially factor and solve commands, are more important. But for calculus 2, a part command is useful. It's usually not as important as factor command or solve command or simplify command, but for calculus it is useful. For example, if you want to decompose a certain rational function by partial fraction, and what do you usually do? Factor the denominator, set up the equation, and then do some algebraic manipulation, compare the coefficient, set up the system of linear equations. Oh my goodness, that's taking really a long time. But if you use a part command, and you can find out the decomposition by partial fraction rather easily. 4x, let me just cook up something, to the 5th power minus 3x to the 4th power plus 2x squared minus 3x plus 1 over 3x cubed minus 2x squared plus 5x minus 2. Will it work? Minus 4. Let's make it like this. I think this will work. And then, well, it produced decomposition by partial fraction, kind of like this. Mathematica use its own order of writings, so it's a little bit difficult to understand. Let me expand the font a little bit. It has quotient part 4/3 x squared minus 1/9 x minus 14 over 27. That's the quotient part. And then decomposition by partial fraction is this plus that. Okay. Well, I just cooked up the problem kind of like this, so probably this was not as simple as, and it would have been as if a problem that was already well written. So let's copy and paste this part and then run a part command, and then let's see what happens. Well, we have something like that. Okay, this wasn't really simple either in the end. Okay. Will this improve? Okay, that certainly improved, at least the way it looks in the end. A part command handled decomposition by partial fraction like these. Finally, simplification is also a very useful command. Let me explain it through 1.3b here. Okay, you can calculate the antiderivative of cosine to the 5th power like this, using the kind of techniques we used in 7.2. Cosine to the 4th power times another cosine, and then cosine to the 4th power can be rewritten as a function of sine function, kind of like this. And then in the end, we have the answer like this: sine of x minus 2/3 sine cubed of x, and so on and so forth. But if I run this command using Mathematica like this, we have an answer like this. Actually, if this is not what I really like, let's rewrite this using basic math assistance. So rewrite it, and then cosine of x to the 5th power dx, and then run it, and okay, we get something like that. Now let's compare Mathematica's response and then the computation we did. Let's compare those. They are supposed to be the same, but are they? Well, one way to do that, one way to see the difference, is to use the simplify command. So simplify, simplify, and then parenthesis open this expression minus parenthesis open sine of x minus 2/3 sine of x cubed minus plus 1/5 sine of x to the 5th power, no, 5th power. And let's simplify this minus that. And if these two are the same, simplification will have to be 0. And are they the same? Well, indeed. So simplify command can be used to verify your computation with Mathematica's computation like this. There are many other ways to do that. One is actually starting from your answer and take the derivative. Oops. And then do we have the integrand back? Ooh, okay. Looks like, okay, this one also raised another question. It generated an answer like this, and is it really the same as cosine to the 5th power? Looks like the simplify command is really useful after all. Simplify. This one. And then minus cosine of x to the 5th power, and then again we got 0, so they are the same. So we just used how useful simplify command can be. And of course you can use simplify command for algebraic manipulation as well. You can do all kind of computation, and in the end you want to find out simplification, just use simplify command, and it'll do, well, a lot of things. It'll make a lot of things much simpler. There are, of course, a lot of other Mathematica commands too, but these syntaxes in section 1 will be sufficient to give you a head up in calculus 2. Actually, even these are more than enough actually. But for the students who are interested in going even further, I put couple more sections about basic programming with Mathematica, how to define variables and define functions, and then how to plot graphs, and then how to manipulate all those plots and all those kind of things, and then get a program. And of course these are extremely simple programs. The kind of programs that I use for 3D graphs are far more complicated. Let me show you. Okay, I opened up another notebook. I hope everybody remembers this. This one is about visualizing the solid of revolution with nice 3D picture with some manipulation. But if you look at the program, as you can see, it's a lot more complicated than kind of things we have seen before. And this is actually only a second half of the program. The first half is even longer. And to do all those kind of things, will require a lot of exercises, and you can start from here right now.